The development of the chemical process now known as the Wacker process began in 1956 at Wacker Chemie. At the time, many industrial compounds were produced from acetylene, derived from calcium carbide, an expensive and environmentally unfriendly technology. Hey, let's talk about Wacker process. It's an olefin oxidation. We have our terminal alkene and we need to convert that to a ketone. Basically, this double bond is going to break and you're going to form that carbonyl right here. What do we need? A catalyst, which is palladium chloride, a nucleophile, which is water, and all nucleophiles are electron donor. Then we need copper chloride and oxygen to regenerate this palladium back. Alright, let's start. So we start with palladium chloride, which is water insoluble. We have to make it water soluble. So we get this 2 chlorine, which are in the solution, and it's gonna come and attach to this complex. So the first step is complex formation. These 2 chlorine are now coordinating with that. Our second step is alkene coordination, where a terminal alkene comes in and a chloride ion is expelled. Remember, the coordination happened like this. So it's coordinating in between. It's not going to coordinate on the terminal side or right here, but it's going to be in between. Third thing is, or step 3 is ligand exchange, where water is going to come in and chlorine is going to be expelled out. So now it's going to coordinate like that. Fourth step is nucleophilic attack. We have water, so water comes in again, but instead of coordinating here or expelling any more chlorine, we have a good electrophile, which is this alkene right here. So it's going to attack, this water is going to attack right here. Why doesn't it attack here and it only attacks here? The reason is secondary carbocation is more stable than primary carbocation. So the water is going to attack itself and it's going to form something like that. Step 5 is rate determining step. So here we have palladium 2 and it goes and turns it into palladium 1. And this is the rate determining step where a chlorine is expelled out. Without this, the cycle won't proceed. So now you have this hydrogen and you have 2 carbons. Carbon which is coordinating to palladium is alpha, and a carbon which is next to it is going to be beta. So now you're going to get beta hydride elimination, where this hydrogen is going to break its bond and it's going to coordinate with palladium, and this where you had coordination, it's going to break and you're going to form that double bond. So you're going to get something like this. So 7th step is going to be 1,2 insertion, where this hydrogen, which is coordinating with palladium, is going to be grabbed by this double bond and it's going to break. But instead of, how we had palladium coordinating on the alpha carbon, now you're going to have palladium coordinating with the beta carbon. So now you're going to have this. So this is the complex you're going to get. So it's coordinating with the tertiary carbon. Now that carbon is alpha to palladium and that oxygen is beta to palladium. So now the hydrogen which is attached to that oxygen is going to go under beta hydride elimination, where this palladium is going to pick up that hydrogen. That bond between hydrogen and oxygen is going to break, and now you're going to form that carbonyl, and this is going to break. So it's going to expel out this ketone, HCl and H2O. Once everything is expelled out, palladium becomes palladium 0. So now you have to regenerate this complex back. So how do you do that? You use 2HCl, oxygen and copper chloride, which is going to give you this complex back, and the catalytic cycle continues.